Hi everyone, welcome to our crash course on radicals. My name is Studio Assistant. In this video, you are going to learn a lot of things. We'll learn about the relationship between exponents and radicals, fractional exponents, properties of radicals, the test to know whether the radical is in its simplest form or not. We'll apply the properties of radicals to simplify radical expressions. We'll learn about how to rationalize denominators, about conjugates and how to use conjugates to rationalize denominators, about addition and subtraction of radicals, how to multiply radicals with the same or different indices, how to divide radicals with same or different indices, and finally, how to solve radical equations. So all of this contents in just this one video. So let's begin with the first item in our list, how to simplify radicals. First, a radical expression is simply an expression containing radical symbol. For example, square root symbol. Now, in order for you to learn this lesson much better, you need to be able to know first that fractional exponent is equivalent to radical expression. For example, we are already familiar that 3 squared is equal to 9. And we would like to reverse the process and go back to the base 3. We can accomplish that by taking the square root of 9. The square root of 9 is equal to 3. Now, in this case, this 9 becomes the radicand. This exponent 2 becomes the index of the radical, and this base 3 becomes our root. This is now the terminologies that you are going to use when dealing with radical expressions. Let's have another example. Let's say 4/3 we know is equal to 64. Reversing the process, we can get the cube root of 64 to go back to the base 4. In here, 64 is the radicand. This exponent 3 becomes the index of the radical, and this base 4 becomes the root, the cube root of 64. Now, in fractional exponents, it looks like this. The cube root of 64 is equivalent to 64 raised to 1/3. Take note that this index of the radical becomes the denominator of the fractional exponent. The numerator of the fractional exponent is whatever exponent is here. To state that formally, we now say that the base a raised to fractional exponent m over n is equal to the nth root of a raised to m. Notice again that the denominator becomes the index of the radical, and a raised to m becomes our radicand. That is the conversion from fractional exponent to radical expression, and vice versa, from radical expression to numbers in exponential form containing fractional exponents. Now let's demonstrate that using this example. Let's say we have 4 raised to 2/3. To write this in radical form, this 3 becomes the index of the radical, then 4 squared becomes our radicand. These two forms are equivalent. One in exponential form, the other is in radical form. Now let's talk about properties of radicals. Let's talk about the perfect nth factor. When we have the nth root of a raised to n, that is equivalent to a. The proof of this is easily seen using the exponential form. We can write this in fractional exponent as the radicand raised to 1 over whatever is the index of the radical. Then applying properties of exponent, this can be written as a raised to the product of n times 1 over n, applying the power rule of exponents. Then n times 1 over n is equal to 1, so this is just equivalent to, which is now this a here. So that means if you have the perfect nth factor, then that is just equivalent to the base. This is the property that you are going to use a lot in simplifying radicals. Whenever there is an nth factor, then you can eliminate the radical symbol. So let's remember this property. We are going to use that a lot. The other property is called as the product property of radicals. When we have the nth root of a times b, we can separate this as two radicals, the nth root of a times the nth root of b. And when we do multiplication of radicals, we are going to use the converse of this property because you will be given 2 or more radicals, and your task is to simplify that as one radical. Now for the proof of this, we can go back to exponents. The nth root of a times b is equal to a times b all raised to 1 over n. Then you have here a power of a product, which we can write as 2 factors, a raised to 1 over n times b raised to 1 over n. And a raised to 1 over n is equivalent to the nth root of a. B raised to 1 over n can be written as the nth root of b. So that shows that if we have the nth root of a times b, that is equal to the nth root of A times the nth root of B, applying our laws of exponents. Let's remember that property as well, and let's proceed to the last property that we are going to use in this lesson, the quotient property of radicals. When you have the nth root of A over B, that is equal to the nth root of the numerator divided by the nth root of the denominator. We can show that this is true using, again, the exponential form of the number. So the exponential form of this radical at the left side is A over B raised to 1 over n. And here, we have a power of a quotient that we can separate as numerator and denominator. So we have the numerator raised to 1 over n, and we have the denominator raised to the same exponent. And we can write this back in their radical form. So these are the 4 properties of radicals that we are going to use to simplify radicals. But how do we know when a given radical is already in its simplified form or not? There are 3 tests, and these are the 3 tests. Let's begin discussing the first one. No radicands have perfect nth factor other than 1. For example, if you have the square root of 16, this is not yet in its simplest form because there are still perfect nth factor. Notice that 16 can be written as 4 squared. And so, you now have here a case when you have the index and the exponent are the same, which is exactly the form of the perfect nth factor form. Therefore, this can still be simplified as the base A. In this case, our A is 4. So the simplified form of square root of 16 is 4. Another example, let's say we have the cube root of 16. Again, we can write 16 as 2 times 2 times 2 times 2. Since the index here is 3, and there are 3 2's here, that can be written as 2 to the third times the remaining factor. Then, applying now the product property of radical, we can now write this as 2 factors. The cube root of 2 cubed times the cube root of 2. And again, you have here a perfect nth factor, which is simplified as the base 2. And just copy the cube root of 2. This is our simplified form, and this is the form that will help you easily add or subtract radical expressions. And so think of this as your prerequisite in order to perform addition and subtractions of radicals. Next example, let's say we have the square root of 400 m squared n cubed. What is its simplest form? 400 is a big number, so let's get its prime factorization. So 400 is 2 times 200, 200 is 2 times 100, 100 is 2 times 50, 50 is 2 times 25, and 5 is 5 times 5. So the prime factors are 2 to the 4th and 5 squared, and we copy the m squared. This n cubed we split as n squared times n, or n to the first. What's the reason? Take note that the index of the radical here is 2. So we want all these exponents of the numbers in the radicand to be divisible by the index of the radical. Since 3 is not divisible by 2, we split this as exponent 2 and exponent 1 because this n squared has an exponent that is divisible by 2. So to simplify this, we apply the product property, so we can write this as 5 separate radicals, each one corresponding to each of the factors in the radicand. And to simplify this, we go back to the concept of fractional exponent. This is equivalent to 2 raised to 4 halves, or 2 raised to the second. To get this exponent 2, we just divide 4 divided by 2 to get this 2. In here, the exponent 2 and the index 2 will cancel each other out because its quotient is 1. We only have 5 raised to the first, or simply 5. The same explanation for m and n. But for the square root of n squared, there's nothing that we can do to simplify it, so we just copy it. Then, we multiply what can be multiplied. 2 squared is 4 times 5 is 20. M times n is mn, and copy the square root of n. This is now our simplified form that we can use when performing addition or subtraction of radical expressions. So, the answer is letter B. So at this point, we are now done with the first condition to know whether a radical is in its simplest form or not. Let's proceed to the second condition. No radicand contains a fraction. So let's say we are given the 5th root of 2 over x cubed. So obviously, the radicand has a fraction. The radicand is 2 over x cubed. We do not want that to happen. So we need to eliminate this denominator x cubed. So let's proceed by applying first this radical property number 3, the quotient property. We can write this as 2 radicals, the 5th root of 2 as the numerator, and the 5th root of x cubed as the denominator. There's still radical expression in the denominator. So, to eliminate this radical in the denominator, we are going to perform what we call as rationalizing the denominator. To rationalize the denominator, we would like to make the denominator a rational number. And the technique is, you look at the index, it's 5. You look at the exponent of the radicand, that is exponent 3. You need another exponent so that when you add that exponent to 3, the sum would be 5. And that number that you need is exponent 2. Because if you apply the product property of exponent, you copy the common base and you add the exponent. So when you add 3 plus 2, you will get the index 5. But you cannot just multiply the denominator by that number. You have to do the same for the numerator as well. So when you simplify the denominator, it would look like this. You have the fifth root of x cubed times x squared, which is combined as the fifth root of x to the fifth, applying the product property of exponent. And the fifth root of x to the fifth is equal to x according to the perfect nth factor property. So by multiplying the denominator by this quantity, basically what we are doing is we are making our denominator become x. But whatever you did in the denominator, do the same thing as well in the numerator. The reason is this number divided by itself is equal to 1, so you are just multiplying the given radical expression by 1. The value does not change, only the form is being changed. So, simplifying now, multiply the numerators to arrive at this, multiply the denominators to arrive at this. In the numerator, we apply this product property. They have the same indices. We write them as one radical, and we multiplied the radicands a and b, so multiply 2 times x squared to get 2x squared. This is now our simplest form given this radical expression. Notice that the denominator now does not contain radical. Now let's proceed to the third condition. There should be no radicals in the denominator of a fraction. Let's say we are given this fraction, 4 over the square root of x. So the denominator is square root of x. It has radicals, and we don't like radicals in the denominator. So what are we going to do? We are going to rationalize the denominator. So the index here is 2, the exponent is 1, so we need x to the first as well, so that 1 plus 1 becomes the index 2. And do the same thing in the numerator. So simplifying, the numerator becomes 4 times square root of x. The denominator is the square root of x times square root of x, which is equal to the square root of x squared. You add the exponents 1 plus 1. And this is a perfect nth factor because the index is implied to be 2. So the denominator becomes x, and this is now the simplest form. Now another case is when you have binomial in the denominator. The technique to rationalize this is to apply this difference of two squares. When you have the quantity a plus b times the quantity a minus b, that is equal to the difference of a squared minus b squared. So in here, think of this as your factor a minus b. You need another factor a plus b, so that a minus b times a plus b becomes a special product equal to the difference of two squares. And this form is easier to simplify. So we now call these two as conjugates. The form is the quantity a minus b times the quantity a plus b. These are conjugates. And to simplify this now, we apply the special product, so that becomes the square of 3 is 9. The square of the square root of x is x. Notice now that this may look complicated, but its simplified form is simply the square of this, which is 9, and the square of the square root of x, which is x. And you multiply the numerator. 1 times any number is the number, so we just copy 3 plus square root of x. And this is now our simplified form of 1 over 3 minus square root of x. Now let's have some exercises so you can master this lesson. So simplify 7 times the square root of 640x to the fourth. How are we going to simplify this? So you are going to make sure that these 3 tests are met, and you can apply these different properties of radicals. So let's solve this together. Let's note that 640 can be written as 64 times 10. Why 64? Because 64 is a perfect square, meaning we can get its square root. So we can write this as separate radicals using the product property of radicals, and we can simplify each of these radicals. We copy 7, square root of 64 is 8. We copy the square root of 10, and the square root of x to the fourth is x squared. You simply divide 4 by the index 2 to get this exponent 2. Then 7 times 8 is 56, copy x squared, copy square root of 10. That is now our answer. That is letter C. you can simply remove this grouping symbol here. 10 is alone. Next example, negative 9 times the square root of 147k squared. You can apply these different properties of radicals to meet these three conditions. Okay, let's do this together. So we can simplify this by writing 147 as 49 times 3. You are looking for a perfect square so that we can write that outside the square root symbol. Then we can apply the product property of radicals to separate them and simplify. The square root of 49 is 7 and the square root of k squared is this k. The square root of 3 cannot be simplified anymore, so we just copy it. And negative 9 times 7 is negative 63. Copy k, copy the square root of 3. That is now our answer. Let's have another example. We have negative 3 times the 7th root of negative 512x y to the 7th c squared. Again, you can apply these properties of radicals to meet these three conditions. Okay, let's solve this problem together. Notice that negative 512 can be written as negative 2 raised to the 9th. And we can simplify that further as negative 2 to the 7th times 2 squared. The reason why we split this 9 as 7 times 2 is obvious. That's because we have an index of 7 here. There's no problem of having negative here because the index is odd. However, if the index is even, that will result to imaginary number. Then, apply the product property of radicals to separate them, and we simplify. So the 7th root of negative 2 to the 7th is negative 2. The 7th root of 2 squared is just copied. The 7th root of x is just copied as well. The 7th root of y to the 7 becomes this y, and the 7th root of z squared is just copied. So only this part and this part are simplified as these two factors. All the rest are just copied. Then multiply negative 3 times negative 2 times y to get positive 6y. And since all of these have the same indices 7, we write them again as one radical. Just multiply the radicands. 2 squared is 4 times x times c squared. And this is now our final answer, which is letter A. Another example. How do you simplify negative 5 times the cube root of 216 xy to the 8 c to the 8. So again, apply these properties of radicals to meet these three conditions. Let's do this together. So we write this as negative 5 times the cube root of the exponential form of 216 is 6 cubed, and just copy all the rest. Then take note that the index is 3, so we want this 8 and this 8 to be split in such a way that one of the exponents is divisible by 3. So it would look like this now. This y to the 8 becomes y to the 6 times y squared. This z to the 8 becomes c to the 6 times z squared. 6 is divisible by 3, and 6 plus 2 is this 8. 6 plus 2 is this 8. Then apply the product property of radicals to write them in separate radicals, and apply the perfect nth factor as well as the definition of fractional exponents to simplify them. So we copy negative 5. The cube root of 6 cubed is perfect nth factor, that's equal to the base 6. Here, the exponent 6 divided by 3 is 2, so you have y squared. Here, exponent 6 divided by the index 3 is 2, so you have y squared. The same explanation for the cube root of c to the 6, that becomes c squared. And copy the remaining. Then, perform the final simplification. Negative 5 times 6 is negative 30, and copy all the rest. This is now the answer, which is letter B. And one more example containing conjugate. Simplify 5 over 4 square root of x plus square root of 3. Simplify this by multiplying the denominator by its conjugate. And so, this is now what we got. The conjugate of the denominator is 4 square root of 3 minus square root of 3. They are identical except that you have here plus and you have here minus. And the numerator must be the same so that we are just multiplying by 1. Then multiply the numerators and multiply the denominators. To simplify this denominator, we apply this property. So that would be equal to the difference of 2 squares. That means you square this and you square this part and put a minus sign between them. So it's now like this. The square of 4 is 16. The square of the square root of x is x. The square of square root of 3 is 3. And put the minus sign. As simple as that. For the numerator, we simply multiply these two factors. We can still apply the distributive property of multiplication over addition, but for now, this is already an acceptable answer. Now, these skills prepare us for the next lesson, which is about addition and subtraction of radical expressions. So, the main concept here is only like radicals or surds can be added or subtracted. So let's talk about surds first. What are surds? Square root of 2 is a surd, whereas square root of 4 is not a surd. What's the difference between the two? The square root of 4 is equal to a whole number 2, and 2 is a rational number, while the square root of 2 has an approximate value of 1.41421356,237, and this is a non-terminating, non-repeating decimal. In other words, a surd is still an irrational number, whereas some radicals, when simplified, become rational numbers. So those radicals that are simplified as rational numbers, they are not surds, but those radicals that are irrational, they are the surds. And in addition and subtraction of radicals, we are adding the surds. Let me show you what we mean. For example, if you have cube root of 8, this is not a surd because 8 can be written as 2 cube, and the cube root of 2 cube is equal to 2, applying the perfect nth factor property. Whereas, when we are given the cube root of, let's say, 16, the cube root of 16 can be simplified as the cube root of 8 times 2, and applying the product property of radical, this can be written as 2 radicals, and the cube root of 8 is 2, the cube root of 2 is simply cube root of 2. We now think of this as 2 copies of cube root of 2. Cube root of 2 is an irrational number, it cannot be simplified anymore, and the cube root of 16 contains 2 copies of cube root of 2. This is the important preparation when you are adding radicals. You want to know how many copies of surds are there in the given radicals if the radical is still an irrational number. If the radical is converted into rational numbers, there's no problem. You are just adding rational numbers. So, let's have an example. Let's say the problem is square root of 2 plus square root of 2. We know that square root of 2 is a surd, and you can think of this as 1 copy of square root of 2 plus another copy of square root of 2. That is equal to 2 copies of square root of 2. Another example. Let's say we have square root of 2 plus square root of 3. Again, both of them are irrational numbers. They are surds. But since they are different surds, we can no longer add them. And so our answer here is just this binomial. Square root of 2 plus square root of 3 is equal to square root of 2 plus square root of 3, because only like radicals can be added. And these two radicals are not like radicals, so our answer is still the given binomial, square root of 2 plus square root of 3. Next, let's say we are given square root of 2 plus cube root of 2. Notice that the base are the same, but the indices are 3 and 2. So the indices are different. And since the indices are different, these are not like radicals, and therefore there is no simplification that we can do. This is our final answer. Only like radicals can be added. Let's say we have square root of 2 plus square root of 8. Now you might be rejoicing, this is easy. These are unlike radicals. The base 2 and the base 8 are different, so the answer is just whatever is the given. That is wrong. In the case of square root of 8, we can still simplify that. Notice that square root of 8 can be written as square root of 4 times 2. And applying the product property of radicals, we can separate this into 2 radicals. And we know that the square root of 4 is equal to 2, so we can still write this as 2 square root of 2. You now have here 2 copies of square root of 2 and 1 copy of square root of 2. That is equal to 3 copies of square root of 2. That is now what we mean by, that is now the reason why we are learning how to simplify radicals. Because we want to know how many copies of surds are there in case the radical is an irrational number, because only like surds or only like radicals can be added or subtracted. Square root of 2 and square root of 8 are obviously unlike radicals. They are not like radicals. But we are going to attempt to simplify the square root of 8 first in the hope that we can come up with like surds. And if we can come up with like radicals, then we will add how many copies of those surds are there. That is how we add or subtract radical expressions. Let's have another example. Let's say we are given 2 square root of 18 plus 3 square root of 8. Find the sum. And we are given these 4 options. Now to solve this, let's simplify square root of 18 as square root of 9 times 2 and square root of 8 as 4 times 2. To solve this, note that 18 is 9 times 2 and 8 is 4 times 2. Then apply the product property to separate the radicals and simplify whatever can be simplified. And do further simplification, we got 6 square root of 2 here and another 6 square root of 2 at the right. So you have 6 copies of square root of 2 plus another 6 copies of square root of 2. The result is 12 copies of square root of 2, which is letter A. That is how we add radical expressions. Another example, 3 square root of 24 minus square root of 24. This is now subtraction. Now square root of 24 and square root of 24 are like radicals, so we can perform the subtraction right away by noting that we have here 3 copies of square root of 24 minus 1 copy of square root of 24. And the result is 2 copies of square root of 24. And then we perform further simplification because 24 is 4 times 6. Then apply the product property to separate the radicals. And the square root of 4 is equal to 2. So finally we have 4 square root of 6 as our answer. This square root of 4 becomes this 2. And 2 times 2 is 4. So the answer is letter B. Let's have another example. 3 square root of 20 plus 3 square root of 5. Again, we will attempt to simplify square root of 20 because 20 is 4 times 5 and apply product property of radicals. Now this square root of 4 is equal to 2, so you'll have 2 times 2 to get 4 square root of 5 at the left and just copy the right side. So you now have here 4 copies of square root of 5 plus 3 copies of square root of 5, that is equal to 7 copies of square root of 5, which is letter A. Another example, this time we have 3 terms. 2 square root of 96 minus 2 square root of 24 minus 2 square root of 72. One technique of simplifying this is by using the list of perfect squares. You want to write this 96 in such a way that one of the factors would be any of these perfect squares. You want the highest possible perfect square. So in the case of 96, that is this 16 times 6. In the case of 24, that is this 4 times 6. In the case of 72, that is this 36 times 2. This 16, this 4, and this 36 are perfect squares. That means we can get their square root. So the square root of 16 is 4, the square root of 4 is 2, the square root of 36 is 6. All the rest are copied and simplify. 2 times 4 is 8, 2 times 2 is 4, copy the minus sign here. 2 times 6 is 12, copy the minus sign. 2 times 6 is 12, copy the minus sign. Notice that square root of 6 and square root of 6 are like radicals. This square root of 2 is different. So we can only subtract this part here. 8 minus 4 is 4. So you have 4 square root of 6. And copy minus 12 square root of 2. These are different radicals. So this is now our final answer. And that is letter B. Now let's have one more example. 2 square root of 3x cubed plus 5x square root of 3x. So again, the same procedure. Notice that this x cubed can be split as x times x squared. We want one of the exponents to be divisible by the index 2 and just copy the right side. Then we can simplify this by applying the product property of radicals. We write them in separate radicals so that this part here is now a perfect nth factor that is just equivalent to x. So we have 2x, copy all the rest. And you have here the square root of 3x and the square root of 3x. So clearly these are like radicals. All we have to do is add 2x plus 5x and append the common third, square root of 3x. And this is now our final answer. And 2x plus 5x is equal to 7x. So our final answer is 7x times the square root of 3x. Now for further exercises on this lesson, we have here some problems. The answers are already given, so all you have to do is solve this first and verify that you get the correct answer. You can pause the video if necessary. These next 4 examples are medium in difficulty, and another 4 problems. This is categorized as the harder questions. Let's now proceed to multiplication of radical expressions. For multiplication of radical expressions, there are 2 cases. The first case is when the indices are the same, and the second case is when the indices are different. For both of these cases, we are going to use the product law of radicals that says the nth root of the square root of a times b is equal to the nth root of the first factor times the nth root of the second factor. But in the case of multiplication of radicals, we are going to use the converse of this property. because we'll be given two or more radicals and we can write them as one single radical. The main requirement here is the indices must be the same. Now, for different indices, we are going to have additional steps to convert the given radicals with different indices into radicals with the same indices so that we can apply this product property of radicals. Now let's have an example. Let's say we are asked to multiply square root of 2 times square root of 10. The index of square root of 2 is 2. The index of square root of 10 is also 2. Therefore, we can apply the converse of this product law of radicals, and we can now write this as square root of 2 times 10. Now this 10 can be written as 2 times 5, and this 2 squared can now be written as 2 outside the radicals, and we have square root of 5. That is because this part here is a perfect nth factor, which is equivalent to the base 2, and we just copy the square root of 5 still under the radical. So for number 1, 2 square root of 5 is the product of square root of 2 times square root of 10. Let's go to the second example. Let's say we are asked to multiply square root of 6 times square root of 3. Again, the indices are the same, so we can just write them as one radical. Now, 6 can be written as 2 times 3, and we have here 3 squared. Now, applying the product property of radicals, we can write this as 2 separate radicals. Applying the commutative property of multiplications, we can swap the order of square root of 2 and square root of 3 squared. This is a perfect nth factor that is equivalent to 3, and we copy square root of 2. So this is our final answer, which is letter D. Let's go to example number 3. This time we have a monomial times a binomial. So what we are going to do is we are going to distribute the monomial factor to each of the terms of the binomial factor. So let's carry that out. These are the different options. So applying now the distributive property of multiplication over addition, square root of 15 times negative square root of 2 plus the same square root of 15 multiplied to square root of 3. Then here we have the same indices. We can just multiply the radicands 15 and 2 to get 30. The sign is outside the square root symbol. Here, we can just multiply square root of 15 times 3. Simplifying, this 15 is now this 3 times 5, we copy 2. This 15 is 3 times 5, we copy 3. Then in here, you have 2 3's, which can be written as 3 squared. Here, there's nothing more that we can simplify, so we just multiply 3 times 5 times 2 to get 30 in the radicand. Here, 3 squared times 5. And applying again the product property of radicals, we can write this as 2 separate radicals. And the square root of this 3 squared is equal to 3. And we just copy square root of 5. Another example. Negative 3 square root of 5 times the binomial 5 plus square root of 10. These are the 4 options. So here we are going to apply again the distributive property of multiplication over addition to arrive at this result. Then negative 3 times 5 is negative 15. Copy square root of 5. Then simplify this part by writing square root of 5 times square root of 10 as just one single radical with the radicands 5 and 10 as the product under the radical. Now this 10 is 2 times 5, so we can simplify this further this way, and you have 5 squared. The square root of 5 squared is 5, so this is further simplified as 3 times 5, and what's left is square root of 2. This part here is negative 15, and this is now our final answer. So the answer is letter C. Now let's proceed to the second case when the indices are different. Here is an example. Square root of 5 times cube root of 2. In this form, we cannot use the product property of radicals because the indices are different. We have 3 and 2. So what are we going to do? We are going to convert these two radicals into like radicals by getting the lowest common multiple of this index 2 and this index. The multiples of 2 are 2, 4, 6, 8, 10, 12, and so on. The multiples of 3 are 3, 6, 9, 12, and so on. We are only after the lowest common multiple. So 6 and 6 are common, 12 and 12 are common, but we want only the least, the lowest common multiple. So we want to convert these two radicals so that both of them are sixth root. Sixth root of something times sixth root of something. Now, how can we find what is the radicand? Notice that in order to get 6, we need to multiply this original index of 2 by 3, because 2 times 3 is 6. Since we multiply the index by 3, we are going to multiply also the exponent of the radicand by the same number 3. For the second radical, from the original index of 3, in order to get 6, we multiply 3 by 2. And since we multiply the index by 2, we are going to multiply also the exponent by the same number 2. I would like you to see the difference. Here we multiply by 3 both the index and the exponent of the radicand, while here we multiply the index and the exponent of the radicand by 2. And by doing so, we now have the 6th root of 5 cubed times the 6th root of 2 squared. Now here the indices are the same, so we can now apply this radical property. We can now write this as one single radical, the 6th root of 5 cubed times 2 squared. Now all the exponents inside the radical are less than the index. That means there is no more perfect nth factor. There's no more radical in the denominator, so this is now in the simplest form. Let's just find the value of 5 cubed to be 125. 2 squared is 4. So finally the answer is the 6th root of 500. And this is now our answer. Let's have another example. Let's say we have the cube root of ab squared times the 4th root of a squared b. Here, the indices are 3 and 4 and they are obviously different. So we need to convert these radicals into radicals with the same indices by getting the LCM of 3 and 4. The multiples of 3 are 3, 6, 9, 12, 15, and so on. The multiples of 4 are 4, 8, 12, 16, and so on. We are after the lowest common multiple, and that is 12. So we want these given radicals to be the 12th root of something times the 12th root of another radicand. So to get the number inside the radical, we now proceed this way. From 3 to get 12, we need to multiply the index by 4. So multiply the index by 4, multiply the exponents by 4 as well. For this 4 to become 12, we need to multiply it by 3. So we multiply this by 3, multiply the exponents also by 3. We just have to simplify to arrive at the 12th root of a to the 4th, b to the 8th, times the 12th root of a to the 6th, b to the 3rd. Now here the indices are the same, so we can now apply the product property of radicals, and we can write this as one radical. We now have here a to the 4th times a to the 6th. That is now what we have here. B to the 8th times b cubed is now this part, both under the 12th root. Then simplify. Notice that here you have the same base. We will just add the exponent. 4 plus 6 equals 10. The same explanation for b to the 8 times b to the 3rd to get b to the 11. Now 10 is less than 12, 11 is less than 12. That means there's no more perfect nth factor. So this is now our final answer. Now at this point, let's proceed to division of radicals. Again, for division of radicals, there are two cases as well. One is when you have the same indices. The second one is when the indices are different. And for both cases in division of radicals, we are going to use the quotient law of radicals that says the nth root of a over b is equal to the nth root of the numerator over the nth root of the denominator. Don't forget to always rationalize the denominator. This is very, very important. Here's our first example for division of radicals. Let's say we are asked to divide square root of 8 divided by square root of 2. So, applying now the quotient law of radicals, since the indices are the same, we can write this as one radical, the square root of 8 divided by 2. And 8 divided by 2 is 4, and the square root of 4 is 2. So the problem is now solved. Another example. Let's say we are going to divide square root of 12 divided by 2 square root of 16. So to solve this problem, we are going to apply again the quotient law of radicals. But let's simplify first 12 by writing it as 3 times 4, and square root of 16 is equal to 4. So simplifying, the square root of 4 is equal to 2. So you now have here 2 outside the radical symbol. And what's left is square root of 3. And at the denominator, you have 2 times 4, which is 8. This is letter D. Next problem. 3 square root of 2 over 4 square root of 8. And these are the 4 options. Let's solve this together. So we have to applying the quotient law of radicals. Since the indices are the same, we can write this as square root of 2 over 8 this way. Just copy 3/4. Then 2 over 8 can be simplified as 1/4. The square root of 1 is 1, the square root of 4 is 2, so you have 1/2. So 1/2, copy 3/4. And finally, multiply 3 times 1 to get 3, 4 times 2 to get 8. Example number 4. Let's say we are asked to divide 4 times the square root of 4x cubed over 3 times the square root of 12x to the 4th. And these are the 4 options. Now, before applying the quotient law of radicals, Notice that this 4 is a perfect square. This x cubed can be written as x squared times x to the first, and x squared is a perfect nth factor. The same here, 12 can be written as 3 times 4, and 4 is a perfect square, and x to the fourth is also a perfect square. So we are going to do this simplification first before we apply the quotient law of radicals. So this x cubed is now written as x squared times x to the first. This 12 is now written as 3 times 4. Then simplify. The square root of this 4 is this 2. The square root of this x squared is now this x. What's left is the square root of x to the first, or the square root of x. Then in the denominator, we copy the 3, but the square root of this 4 is now this 2, and the square root of x to the fourth is now this x squared. So what's left is square root of 3. Now notice that 2 and 2 are common, and 2 divided by 2 is equal to 1. X divided by x squared is 1 over x. So you have x here. So 4 times 1 times square root of x is 4 square root of x. 3 times x times square root of 3 is 3x square root of 3. But this is not yet our final answer because there's still a square root of 3 in the denominator. So we rationalize the denominator by multiplying both the numerator and the denominator by square root of 3. Because square root of 3 times itself is equal to 3. And so in the denominator, we have 3x times 3, which is equal to 9x. And then we just simplify the numerator. 4 times square root of 3x over 9x. And that is letter A. Here's another problem. We now have here a binomial divided by a monomial. In this case, we are going to divide each of the terms in the numerator by the monomial divisor. So this looks like this. Square root of 16 divided by square root of 8 minus square root of 32 divided by square root of 8. Then you simplify term by term. Square root of 16 divided by square root of 8 can now be written as square root of 2 because 16 divided by 8 is 2. Their indices are the same, so you can divide 16 over 8. Now here, 32 divided by 8 is 4, so this is square root of 4. We know that the square root of 4 is equal to 2, so this still can be simplified as square root of 2 minus 2, and this is our answer. Now, let's take a look at where we are so far. We are in division of radicals with the same indices, and we talk about the case when you have one term in the numerator and one term in the denominator, and we just saw a binomial over a monomial in the previous example. There's still a case where you have multinomial over multinomial. We are already done with these first two. The example of the first case is when you have square root of 8 over square root of 2. The example of the second case is square root of 16 minus square root of 32 over square root of 8. Now this last part here is more complicated, and we are going to have an example of that later. We now move first to division when the indices of the radicals are different. Here is the example. Again, we are going to use the quotient law of radicals. Let's say we have square root of 2 over cube root of 2. Again, the idea here is we still use the same quotient law of radicals. We are just adding some more steps to convert these radicals with different indices into radicals with the same indices so that we can apply the property. So we want to get the LCM of the indices 2 and 3. Multiples of 2 are 2, 4, 6, 8, 10. Of 3 are 3, 6, 9, 12. We want the lowest common multiple, and that is 6. So we want now to write this as the sixth root of something divided by the sixth root of something. The same with multiplication. In order to get the sixth root here, we need to multiply this 2 by 3 to get 6. So multiply the index by 3, but multiply also the exponent of the radicand by 3. For the denominator, for this 3 to become 6, we have to multiply by 2. So multiply the index by 2 and multiply the exponent of the radicand by the same number 2. In that way, both are in the sixth root now. So we have the sixth root of 2 cubed times the sixth root of 2 squared. Since their indices now are the same, we can now apply the quotient law of radicals and write them as one radical. So we have the sixth root of 2 cubed over 2 squared. So applying the quotient law of exponents to divide 2 cubed by 2 squared, we copy the common base 2 and subtract the exponents 3 and 2. And so the final answer is the sixth root of 2. Let's have another example. The cube root of x squared divided by the fifth root of x. So again, we need to get the LCM of 3 and 5, and we want the lowest common multiple. The lowest common multiple is 15. So we need to rewrite the given radicals to both 15th roots. From 15 to get 3, we need to multiply by 5. From 15 to get 5, we need to multiply by 3. So here is now the result. For the numerator, we multiply the index and the exponent of the radicand by 5. For the denominator, we multiply the index by 3. And we also multiply the exponent of the radicand by 3. Then we simplify. Now, since the indices are the same, we can now apply the quotient law of radicals, and we can write this as a single radical, the 15th root of x to the 10th divided by x to the 3rd, which is equal to the 15th root of x to the 7th, and that is now our final answer. Now, let's have another example. So again here, the indices are different. We have 6 and 8, so we need to get their LCM. So here are the multiples of 6 and 8, and the lowest common multiple is 24. So, convert the given radicals into the same radicals, both with 24 as the index. To get 24 from 6, we need to multiply by 4. To get 24 from 8, we need to multiply by 3. Then simplify. Now here, this still looks complicated, but let's apply now the quotient law of radicals. We can write this as a single radical. Then you have here division of polynomials. A monomial divided by a monomial. All we have to do is to line up the same variables and subtract their corresponding exponents. So, x to the 16th divided by x to the 21 is x to the negative 5, or we can write that as 1 over x to the 5th. We do not need to write the 1 because there are still other factors here. Y to the 12th divided by y to the 6th is y to the 6th. Z to the 8th divided by z to the 3rd is z to the 5th. Then write this concisely. There's still a problem here. We still have a denominator of x to the 5th, so we have to rationalize the denominator. Notice that the index is 24, the exponent is 5. From 5 to get 24, we need 19. So we need to multiply both sides by x to the 19th. So that x to the 5th times x to the 19th is equal to x to the 24th. Just multiply the numerators. X to the 19, copy y to the 6, copy z to the 5th. But the 24th root of x to the 24th is x. So we are now free with radical in the denominator. So we can now simplify this as the 24th root of x to the 19th, y to the 6th, z to the 5th, all over x. The denominator is now a rational number. This is now our answer. Now, let's have a case when you have multinomial over a multinomial. This is a harder case. Again, the idea here is we want to rationalize the denominator, and we need to recall the difference of two squares, or the special product, the product of the sum and difference of two numbers. We are doing this so that we can eliminate the radicals in the denominator. At the same time, the result would be easier to complete. The computation would be easier to do because we have a special product. So let's multiply both the numerator and the denominator by the conjugate of the denominator. This is the denominator. Our a is negative 3x squared. So our a here also is negative 3x squared. One is minus, one is plus. Our b is 2 squared of 2x, so you have the same 2 squared of 2x here, and we copy the same in the numerator. Then performing now the multiplication, we multiply the numerators, we just copy them here, but the denominator is a difference of 2 squares. All you have to do is just square a. So we have to square this part here to get this now. That is squared. Minus, this is the minus, b squared. And our b is this part. Just copy that here and square that one. Then from here, all the rest are just simplification. So here you have a binomial times a binomial. You are going to distribute this 4 times, like this, and then this one, multiply there, like that. So applying now the FOIL method, we arrive at this numerator here, and we are going to square the denominator. So square of negative 3 is 9. Square of x squared is x to the 4th. Copy the minus sign. Square 2 to get 4. And then you square the square root of 2x, you will cancel the square root. So that 4 times this 2 here becomes 8. And we copy the x. Then there's a common factor of x both in the numerator and in the denominator. So let's factor them out. We now have this x factored out. So we can cancel this out. So the final answer would be this entire thing here divided by this binomial here. Square root of 2x and square root of 2x are the same, so this can be considered as like terms. We can still combine 4x plus 6x squared to arrive at this. But this part here is already considered as the final answer. If you write it one more step this way, that's also correct. Notice that for multinomial divided by a multinomial, it's getting more difficult. So at this point, let's now proceed to solving radical equations. Here is the problem. Solve the equation, the square root of negative 50 plus 15m is equal to m. And here are the options. Now, when solving for radical equations, there are two things that we would like to accomplish. Number one, we would like to isolate the terms with radicals in one side of the equation, whether at the left side or at the right side. But not all the time that is possible. And number two, we would like to eliminate the radicals by raising the equation to a power. Let's remember that radicals are fractional exponents. So when we have square root, that means the radicand can be raised to fractional exponent 1/2. And to eliminate the radical, we want to make this fractional exponent a whole number. For example, in here, what number are you going to multiply to 1/2 so that you can get 1? The answer is its reciprocal. That is why, going back to our problem, in order to eliminate this square root, we are going to raise both sides of the equation to 2. The fractional exponent of 1/2 that is equivalent to this square root times this exponent 2, that would result to exponent 1. And so by raising both sides of this equation to the second, we canceled out this square root. What's left would be this radicand, negative 50 plus 15m, and we just copy the right side. So the resulting equation now is quadratic. So let's gather all the terms at the right side by adding 50 minus 15m to both sides of the equation. Here, the left side becomes 0, and the right side becomes m squared plus 50 minus 15m. And then let's rearrange this in descending order of power. We now have here a standard quadratic equation. You can solve this in any manner you want, either by factoring, by quadratic equation, or any other method that you already know. So in this case, let's solve this by factoring. We need the factors of m squared and the factors of 50. M squared is m times m, so we write m times m here. For 50, there are several pairs of factors, but we want the pair in such a way that when you add them, the result is this middle term, negative 15. And so, what we need is negative 10 times negative 5 because the product is positive 50, and the sum is the coefficient of the middle term, negative 15. Therefore, the factors are m minus 10 and m minus 5. So we now have here a product that is equal to 0. So each of the factors is equal to 0. At the left side, we add 10 to both sides of the equation to get 10. At the right side, we add 5 to both sides of the equation to get m equals 5. So there are two answers now here. But this is the important idea behind solving radical equations. When we square both sides of the equation, we are passively introducing an extra root. That's why it's very important that we check the resulting roots of the equation to the original equation before finally deciding what are the solutions of the equation, because there might be extra roots. So let's now check the original equation when m equals 10 and when m equals 5. So when m equals 10, we arrive at the square root of 100 equals 10, which is correct. When m is 5, substituting this 5 to m, we arrive at square root of 25 equals 5, which is also correct. So in this case, there is no extra root. The final answer is letter B, m equals 10 and m equals 5. Both will make this equation true. In the next video, we are going to look for the cases when there are extra roots. Solve this radical equation. The square root of 3x minus 5 plus the square root of x minus 1 is equal to 2. This problem is considered hard because, number one, there are two radical expressions here. And number two, this is the type of radical equation that has extra root. So let's do this together. First, let's recall that there are two things that we would like to accomplish when we are solving a radical equation. Number one, we want to isolate the terms with radical in one side of the equation. But our problem here is there are two terms with radicals. So that means we are going to apply this number one condition 2 times. And number two, we would like to eliminate the radicals by raising the equation to a power. And we are going to apply this number 2 also 2 times because there are two radicals in this equation. So let's start by eliminating one of the radicals. And let's do that by isolating first the square root of 3x minus 5 at the left side of the equation. That means all the other terms should be at the right side. Then, to eliminate this square root, we square both sides of the equation, and this is what we have. So the left side is raised to the second, and the entire terms at the right side is also raised to the second. Then this square root and this exponent 2 will cancel each other out. So our left side is now 3x minus 5, but the right side would still contain radical, because when we square this binomial, the result would be the square of the first term is 2 squared or 4, then twice the product of the first and the second terms, so 2 times 2 times square root of x minus 1 is 4 times the square root of x minus 1. We copy the minus sign. Then we square the second term. That would be easier because we will be able to eliminate the square root and the exponent 2. So we have x minus 1. Then let's gather all those like terms, and this is what we have. We have this 3x, this plus x here becomes minus x at the left. We copy the minus 5. Then this plus 4 here becomes minus 4 at the left side of the equation. And this minus 1 becomes plus 1. At the right side, we have negative 4 times the square root of x minus 1. Then combine like terms to get 3x minus x equals 2x. Minus 5 minus 4 is minus 9 plus 1, that's minus 8. Then copy the right side. Then we can divide each of the terms of this equation by 2 to simplify the equation to x minus 4 equals negative 2 times the square root of x minus 1. We now have here a simpler equation but still containing radical. So we are now going to apply again the same procedure. We are going to raise both sides of the equation to exponent 2 so that we can eliminate this radical at the right side. So we have here a square of a binomial which is expanded as x squared minus 8x plus 16. To square a binomial, we square the first term, copy the sign, then get twice the product of x and 4, which is 8x, then square 4 to get 16. At the right side, you square each of these factors. So the square of negative 2 is positive 4. The square of the square root of x minus 1 is x minus 1, because we'll cancel out the square root and this exponent 2. Then we distribute 4 to x minus 1 to get 4x minus 4. Then again, we gather all like terms in one side of the equation because we have a quadratic equation here. This 4x at the right becomes minus 4x here at the left. This minus 4 becomes plus 4. All the rest are just copied. And then simplify. Copy x squared minus 8x minus 4x is minus 12x. 16 plus 4 is 20. Then we now solve this quadratic equation. Notice that there is no longer radicals. And we know how to solve quadratic equation. In this case, we are going to use factoring. So we need to find what are the factors of x squared. We know it's x times x. Now, what are the factors of 20 such that when added will result to negative 12? Those factors are negative 10 and negative 2. When multiplied, the result is positive 20. When added, the result is negative 12. We now have two factors, x minus 10 and x minus 2. The product of these two factors is 0, so each one of them can be equated to 0. And adding 10 to both sides of the equation, we get x equals 10 here. And at the other side, we add 2 to get x equals 2. Now, we need to check for extra roots. So we have to go back to the original equation and check whether x equals 10 or x equals 2 or both of them will make this original equation true. So let's take first x equals 10. Substitute 10 for x. So this x becomes 10. This x becomes 10. Then 3 times 10 is 30. Minus 5 is 25. So we have square root of 25. Then 10 minus 1 is 9. So you have square root of 9 here. And the square root of 25 is 5. The square root of 9 is 3. 5 plus 3 is 8, which is not equal to 2. This is wrong. So therefore, x equals 10 is our extra root. That is not our answer. So let's check x equals 2. Again, substitute 2 for x. This x becomes 2. This x becomes 2. 3 times 2 is 6. Minus 5 is 1. So you have square root of 1. And 2 minus 1 is also 1. So you have square root of 1 here also. And the square root of 1 is 1. The square root of 1 is 1. And 1 plus 1 is equal to 2. And this is correct. So our correct answer is x equals 2. And this problem is now solved. So thank you very much. This is Lando Assistant. We hope to see you again in our next video. Bye for now.